Hello.
Hello, sir.
Yeah. So you can hear me?
Yes, sir.
Yeah. Before I start today's class, any questions, doubts, anything that was done so far? Okay. So if not, maybe we can just quickly kind of recap what all things that we have done. So in the last class, we were last class, we kind of partitioned this set of problems. There was three techniques in some sense. There was this greedy algorithms. There was this recursive algorithms or divide and conquer algorithms, whatever you want to call. Conquer algorithms. This is basically in some sense, is recursive. You kind of use this, break it up into smaller ones, and then solve it. And then there was the dynamic programming. Now we have not seen dynamic programming per se as such, except for one small example, possibly. So in mm, the greedy algorithms, what you have seen is you have seen the say the shortest path problems, shortest path algorithms. You have seen the MST, the Prim's algorithms. You have also seen in the last class this perceptron algorithms, and you also have seen beforehand things like insertion sort and so on. Now there are some more algorithms, or rather quite a lot of more algorithms in this greedy algorithm framework, and I would not be able to solve or go over all of them. So I would insist that you guys just take a look at some of the books in which what are they saying, what are defined algorithms that they're talking about, and so on. And basically, uh, uh, mm, so and also we will be uploading a set of assignments and problem sets which will be introduced to some more problems in this direction. The other thing that you have is this divide and conquer algorithm. So this also we have not done much, honestly speaking. We have this merge sort and the quick sort. And there were some parts that were done a little bit in some sense. So we had kind of talked about sorry, we have this median finding that you had median finding. And again, there are quite a few of the other ones that we are kind of skipping here. So one of them was the matrix multiplication. We have talked about it a little bit, and if I have time, I will talk about it later on. And there is also this how to multiply two big numbers and so on. So there are examples of this. And we have this dynamic programming. You have seen a little bit of it in the Floyd Warshall or Bellman-Ford kind of stuff like that. But so today we will be looking at this dynamic programming in a bit more classical setting, in which where you will possibly get a better feel of this whole thing. So this is so let me just quickly jump into what is it that we want to, or what is the problem that we want to try to solve, and how we can use it for that. Okay, so this problem is called the longest common subsequence problem, and this is a problem that actually arises in many real life applications, including gene editing and gene sequencing and all of those kind of stuff like that. So basically, what is the sequence, right? So yeah, so basically you have a sequence is basically a kind of a huge string of numbers. Okay, so you can think of, like in the case of you can think of this English words, or if you want to talk about this gene, then it's a string of say A, G, C, T, say it's 10,000 length string of this form, right? So this is a sequence. So sequence is nothing but a big number, a big length, a big word of comprising of certain number of symbols, and it goes on like this. Say I have A, G, G, C, T, T, G, C, A, T, G, C, and so on. Right? So that can be a sequence. Now, what is a subsequence? So subsequence is nothing but a sum of them. Okay, so like this one, so I can say, okay, let me check G, G, T, G, A, T, C. So this is a subsequence. So subsequence, it doesn't have to be contiguous. Okay, it is just a subset of this sequence. So you can drop some of the letters of the sequence and you can get a subsequence of that sequence. Okay, now the problem that we are looking at is what is known as the longest common subsequence. So you have been given two strings. So I have a string 1 and string 2. Say here it is a G, G, C, T, T, G, C, A, T, G, C. And the another one is G, A, C, G, T, C, A, G. Now, what is the longest? What is the common subsequence? So, common subsequence is nothing but a sequence that is available in both of them. So, for example, I can say that, okay, I can take this G, C, T, A, G. The G, C, T, A, G. So this is a subsequence that is there in string 2. This is a subsequence that is there in string 1. And so this subsequence is available in both of these things. So this is a common subsequence. Now, of course, there can be bigger one than that. I mean, I don't even know here, is there something bigger? Is there something bigger here? You can take a look at it.
Yes, sir. You can include the last C in the second string.
In the second string, I can include the last C.
Yes, sir.
So you are saying that I can include this C,
And
T and okay, here, right? Okay, good.
yes, sir.
So that can be that is a longer subsequence.
You can also include another G.
I can also include.
Oh no, that will be possible.
G.
No, sir. No.
Actually, there can be, I can do something crazier. Let me see. No, GA. I mean, I could have taken, say, this AG. I can take A.
No, the C comes before that. So
The AG instead of this 2, but then that doesn't increase the sequence length, right? Yeah, so basically it's not very clear. As you can see, it's not obvious what is the longest common subsequence. We might have to really look at this one very carefully to find out, is there something longer? Right. So is the problem clear at least? So the problem is basically you have this two sequences, okay, and your job is to, so here is, I have drawn it in two different ways. I have two strings. Say mathematics is one string, education is one string, and I'm asking, okay, so in this case the longest common subsequence is EATI. It seems EATI. EATI. Okay. Now, is this the longest common subsequence? It's, I mean, that's what I claim here. Maybe there's something longer than that. Okay, so similarly here, this in the string, say villages and cities, what is the longest common subsequence? I think it is should be EIS, right? IES basically. This is IES and this is I and ES. I think this is the longest common subsequence here.
Yes, that will be no.
Right. Right. So this particular problem of is very important in the computational biology world. Okay, it is kind of yeah. Go ahead.
So just wanted to ask, so finding the longest common subsequence doesn't tell us if two are related, right? So we also need to consider the pattern of indices should be same. If we wanted to say something about the genome of the
No,
gene
so
expression.
see, it is not about the genome of two strings. Okay, so how is this genomes are done is something very. So how is the genome sequence done? If you go into details of that, what happens is that they break the gene into small parts.
Yes, sir.
Okay, and then they try to find out so they will then get a lots of this. They can decode all the small parts, right? And then their job is to kind of place the small parts in the correct place where it can be placed.
So
Yes.
the longest common subsequence will be indicative of maybe a common ancestry in both of them. And
No,
then
that
they
is
can-
one option. That is one way of doing it, but that is slightly different. There is something called a phylogenetic trees, which is related to that.
Okay.
So,
So,
but that's yeah. So yeah, go ahead.
yes, I was just saying that if the indices are not in the same pattern of the longest common subsequence, then we cannot really say anything. So
No, why not?
right. So because whatever so after doing the gene sequencing,
Yes.
so
I mean, there might be
we-
there something might have been added. Some genes gets added, right? Some things
sir.
get added. They could become longer and smaller and all.
yes, sir. So that's why so there would be chunks of things that would be somewhat very good match, and in that chunks we can say that the patterns are same, then we can conclude something. But I don't think that for
So
the
the
whole
way in which it is done is that okay. So this is how okay. So what say we want to sequence your DNA. Okay. How will we sequence it? We will split your DNA into small chunks. Okay. In a small container, your DNA has been split into small chunks. Okay. Now say I get to know that one of your small chunks is of a particular string. How do I know where does it come from? Does it come from the beginning of the string or the end of the string, or somewhere in the middle?
so for
yes. So for that, what they do
we
is that
we try to overlap the things and
you try to overlap the things. You look at the gene sequencing. So there are few human beings whose gene has been sequenced very carefully.
yes,
okay,
sir.
And then they try to match that part, okay, with
Yes,
that
sir.
gene. Okay, in which part of the gene does it match perfectly, or as perfectly as you can? So with the full gene sequence that has been there of a person, okay, some person, and with your small chunk, okay, they try to find out the longest common subsequence of that gene and your gene. Wherever the longest common subsequence is, they will say that okay, so I think it goes there.
So can we also do some sort of analysis of what is the distribution of the longest common subsequence in if all the genomes were random, and then
Yeah,
if we
so-
see that between two of them we are having longer common sequences which are on the higher end of that distribution, then we know that that's significant in some sense.
That is also done to some level, of course, because they have this whole things about. So I mean, these are of course. I mean, the actual genome sequence is a much more complicated process. Okay.
Right.
Yeah, but so here what I'm saying is that when we are actually sequencing a genome, which is actually a very hard job to do. Okay.
Okay.
Same thing for say if you find out you want to sequence the genome of a monkey. Okay. Now we kind of know that the monkeys are related to us,
Right.
but when we genome, see, it is not that you put that monkey cell in a container and the whole sequence comes out. That doesn't
Right.
happen like that.
Okay. Okay.
Okay, so it
Right.
is kind of the whole sequence of the chemical compound is broken into small chunks. Small meaning not very small, but small enough. Okay, so instead of say maybe 1 billion base pairs, it is you have got 10,000 base pairs each.
Okay.
Okay, now and it can be split up in some random way. Okay, so it's not like all of them the first 1,000, then the next 1,000. No, I mean it's like you get split up in somewhere in the middle. Okay, so now you have so what you get is say so you have this monkey, so this monkey gene that you are looking at, and you say that okay, one of the gene is of a form say A G G C T A. Okay, that's one small thing. You have no idea whether this gene, this part of the monkey, is coming in the beginning of the whole gene sequence or the end or where.
Right.
Because you have no idea because it's kind of got split over here.
Okay.
Okay.
Yes.
Now,
So
how do you place it?
so that's why I was thinking of maintaining the pattern of the chunks that we are taking. So
But you have no idea whether that patterns exist or not. The monkey versus human, right?
oh,
So the-
okay, sir. So if we
So one way of doing it is to look at the human genome sequence. Okay. So maybe the human genome sequence, one particular human genome sequence, and then look at okay, somewhere here
You're having
it
a strong
doesn't
match.
it doesn't match, but maybe there is some GGTA kind of stuff like that or something like that. Okay.
Okay.
I
Right.
mean, okay, so you'll find out the place where this longest common subsequence matches, and that is from where I believe that this is coming.
Okay. Okay.
Okay,
So
of
the
course.
longest common sequence would be one of the factors that we will be assessing. There will be many other things.
There are many other things.
Right.
That's why it is not human genome sequencing is not like a I don't know what a diabetes test kind of stuff. You put it in something and you get it.
Right.
yes.
Okay.
Okay.
Yes,
It's-
so my point was if we are matching these two genomes, so
Yes.
so by pattern I meant that that suppose in both AGTA would be the common thing.
Yes. AGGTA. Will be AGGTA will be a common thing, right? In some sense, we don't know what is it. So the AGGTA is the common thing here.
Oh,
Okay.
okay, sir.
Now you
Yes,
cannot
so-
say so it might very well happen that maybe one thing got changed or removed and then that got added or something. We don't know how it happened. Okay, so we'll come to this one in the next class. Actually, next class we have another problem, which is also similar thing of this, right? But
Okay.
how this change could have happened? What is the easiest way of changing this to this? That's a different question. Okay, but see, this is the longest common subsequence. It doesn't mean it will match or everything or something. Okay, means among all the other places, this is where it matched perfect, best.
Yes.
And you go with that. Now, of course, see, again, there are lots and lots of other things that are done. Okay, scientists don't just do this thing because they have some idea about which gene is required for what and so on and so forth, and lots of this kind of extra information are there.
The indices, so the point changes happen. So here we are considering the shifting can happen.
Yes,
but,
the shift, some deletion can happen.
Yes,
Also,
sir.
some
Okay, sir.
deletion could have happened also.
Okay, sir. Then it's fine. Yes, sir.
Okay. Again, so this is not the final thing, but this is one of the crucial things that are used. Okay, and I'm not saying that if you know this one, you know how to sequence the genome gene. By no way, it's a way more complicated than that. Okay, but Okay, at least for our purpose, we can live with this problem and go ahead. So what is this problem actually now? So we have these two strings, need not be of the same size. One is of size n, one is of some m. Okay, so A1 to AN and B1 to AM, and our job is to compute the longest common subsequence of A1 to AN with P out of A. Now, can you guys think and tell me of any particular technique in which you can do it? If somebody comes up and asks you, can you please find out the longest common subsequence, what will you do? Any technique, anything, even it can be horrible, but that's fine. But let's start with something.
So first so the most basic technique would be, I think, first we start with A1 and find A1 in the second sequence and locate A1. Then we will take A2. Then we will take check the indices after A1 in the second sequence. And in such way, we just mark it, and just finally we will get a common sequence that includes A1. So
Right.
if there is not, and then we go to A2 and do the same thing.
Okay, so you are saying that, okay, so what you will try to do is kind of a brute force kind of thing, right? Find out
Yes.
whether A1 is there. So among the sequences that uses A1, what are the sequences that is there?
Sir, we can take a recursive kind of approach, I guess. So suppose we know that the longest common subsequence of A1, A2 up to AN minus 1 and B1, B2 up to BM minus 1.
Okay, very good.
And then we can check AN and BM.
Okay,
So-
excellent, excellent. Yeah, somebody else was saying something?
Sir, I was saying, wouldn't there be a problem in the correctness of this? Because what if A1 turned, what if there is something like A1, A3, A2 in the second string?
Right?
So if we find A1 first and then we look at A2, then
Yeah,
we will.
so there is no guarantee that the longest common subsequence will contain A1.
So even if it does, I'm saying that this brute force method might not work, because what if, let's say we have in the second sequence, we have A1, A3, A4, A5, A6. If this is the
Right.
second sequence,
Right.
then in this brute force method, what we will find is A1, A2. And that
Yes.
won't be the longest common subsequence. And we know that the longest common subsequence does include A1.
Yeah,
But
so
the-
it's not just A1, you have to completely recursively do it. Okay, so whether it contains A1 and A2 kind of stuff like that.
Okay, right.
Okay.
Sir, if let us say without any loss of generality, can we do this? Let's say if we assume n is greater than n, okay, and then we look at the first for the second, the shortest string, we look at B1, okay, and we mark like, let's say, for example, as you were discussing with genomes, let's say we mark where B1s are,
Right.
okay, and then we break the A string. Like based on the markers. So the point is key. If the longest subsequence that can be present is the B string inside. So if I take B1 and based on B1, I break it the A string, then I have basically sub problems. So I have
Yes, you have sub problems, but you don't even know whether the B1 where you have broken. Okay, so there can be two B1s in the second. I mean, in the second thing, right? I mean, they say B1 is B1 is say T and B5 is also T.
Okay. Yes.
Right. Now you are just marked out all the places where T exists, right?
Okay.
In the A1 to AN, but you don't know whether that T should match with the B1 or B5.
Sir, hello.
Yeah.
Sir, we could try this. We have A1, A2, AN, and B1 to BM.
Yeah.
We find the first occurrence of B1 in the sequence A,
Right.
and mark it. And we find the first occurrence of A1 in the sequence B and mark it.
Okay.
And then we remove A1 and B1 from the respective sequences.
Yes.
And we somehow continue this and append them somehow.
Okay, so that's Okay, now whatever you told, okay, if I understand it correctly, okay, then let's try to see what's going on here. So what is happening here is that you have this, say, A1 to AN, you have B1 to BN. Okay, so let's say A1 equals to A and B1 equals to B, just for the. So you find out which place, say B5, this is the first time where this is equals to A. And you have this A3, this is first time when this is equals to B. And you are saying that, okay, in that case, I would just now look at, try to find out the common sequence between this string and that string.
Yes, and we.
But who guaranteed you that the longest common sequence will actually contain A1 or B1? It might be that here, the string that you have thrown away, and here the string that you thrown away, they have a huge common intersection. Right? And by kind of greedily trying to match A1 with B5 and B1 with A3 or something like that, you are forgetting this chunk.
Okay, so we cannot forget that we have to do it for all the A1, A2.
Yeah, we don't know whether this chunk has common things or not. They might have a lot of common things, right?
Yeah, so we can now create an M cross N matrix of at which point A1 occurs in the list B.
Good. So you are thinking in this way, that's good, okay? So, so let me, so I think many of you are possibly thinking in this right direction. So one thing is that the greedy approach, okay, you have to do it. So there's a two kind of greedy approach. One of the greedy approach is just what you told in some sense, that let's find out where the A1 occurs in P and then throw away everything before that. Or find out where the B1 occurs in A and throw away everything before that. The issue is that with that kind of a greedy approach, it is hard to prove, or you cannot prove that whatever you output is actually longest. You will output, of course, a common subsequence, but why is it longest? Okay, so that is one thing. So there, okay, now you can, so you can, it does become the heuristic algorithm, but you can now start arguing that no, that will give us a string which is long enough or something, but it's not necessarily longest. The other option is actually to do what is called this hardcore brute force, which is consider all possible subsequence of A1 to A. Okay. Now, how many possible subsequences are there? Can you say how many? 2 to the power n possible subsequences, right? Now, if I give you a particular subsequence, I want that this subsequence has to be a part of B1 to Bm. Can you check it?
So we can do the brute force first occurrence method.
Right. Then you can do the brute force first occurrence method, and that will work. So if I guarantee you that, see, here is the subsequence, and either this subsequence is a complete subsequence of the B1 to Bn. So sorry, here's the sequence, okay, and either this sequence is a complete subsequence of B1 to Bn or not. This thing you can check easily by doing the same brute force kind of technique, right? So basically, I have a A1 to An, or sorry, B1 to Bn, right? So B1 to Bn, and I have given you a small subsequence here. Say it is A, G, C, T, A. Now, question is, is this A, G, C, T, A is a subsequence of B1 to Bn? Yes. In that case, what you do? You go and look at the first string, first Bi here, which is equals to A, right? So if this string is a subsequence of B1 to Bn, then this string better be a subsequence of this set. Okay, so A, G, C, T, A is a subsequence of B1 to Bn if and only if GCTA is a subsequence of Bi plus 1 to Bn, where Bi is the first or where I is the smallest index such that Bi equals to G, A. So basically, so I mean, I'm not proving it. I leave it to you to prove it. But this statement is what is. It's not hard to show. And the important thing is that this shows that if I am re-asking that can this be a subsequence of P1 to Pa, this can be done. How? I first find out of the smallest one, then I look at the next one. Okay, once I find something, I will start looking at it and find out the next Bj, which is equal to G, and then I continue like that, right? So it is basically order M steps. In order M steps, you will be able to check whether a particular sequence is a subsequence of another sequence. Okay, but that doesn't prove for the longest common subsequence. So what can we do with the case of this for finding longest common subsequence? One option is find out all possible subsequences of A1 to An. There are 2 to the power n such things, and find out which of them belongs to, which of them are subsequences of B1 to Bm. Right, and by that you will find out the longest common subsequence of A1 to An and B1 to Bm. Is this clear, this algorithm?
Yes, sir.
Yes, sir. It's clear.
Yes.
The problem with this algorithm is that it is time consuming, right? Because you have 2 to the power n possible subsequences of A1 to An. Even if you, for every one of them, you have to take order M steps. So this one time complexity becomes, so order M for any one of them and into 2 to the power n. So this is not a very good time complexity, but this much time, using this much time, you can do a brute force algorithm. Now there might be some other cleverer brute force algorithm. Okay, so this is 2 to the power n actually. Yeah, I mean I have here so runtime is in order 2 to the power n, but it should be m times 2 to the power n. But main important thing is that this time complexity is exponential in the input size. So what can we do? Now this is where I want you guys algorithmically, this is where I want you guys to think. Okay, I think many of you are thinking this way. It is basically recursion. Okay, whenever you have a small problem, okay, so after you kind of have ruled out greedy algorithm, the next thing that you should always think of is, can I break this problem into smaller problems? Or in other words, in some sense, you can say that if somebody has come up with a solution for my smaller problem, then can I do it, right? So it's kind of a recursive kind of a thing. So see, here it is. Say I have an algorithm, which is a LCS, longest common subsequence, the IJ. It finds out the longest common subsequence between A1 to AI, between A1 to AI and B1 to BJ. Right? Now, what can you say? So let's see. Let's say that this is the longest common subsequence. Okay, I'm not writing the algorithm first. I'm trying to understand this whole thing. Okay, how are this LCS IJ related to each other? So what is LCS K0? It is the longest common subsequence between A1 to AK and empty set, empty string. So of course, it is 0 and so on for the case of LCS 0K. Right. Now, say here is it. Okay. Somebody, so I have these two strings, villages and cities, and I want to find out the longest common subsequence. What is it that we want to solve here?
Sir, hello.
Yeah, go ahead.
Sir, what was that I and J? Can you?
Yes, I and J. I is the index between. So I is between any number between 1 and n, and J is any number between 1 and m.
Means what does this denote?
So LCS is the longest common sequence. IJ is the you can say the length of the order if you want. So length of the longest common subsequence between A1 to AI and B1 to BJ.
Okay, sir. Okay, sir. Thank you, sir.
Okay. So it is a smaller problem. Since I is less than n and B is less than m, this is a smaller problem. Correct?
Yes, sir. Here, are we looking for the length or are we also looking for the sequence itself?
I mean, I will present it as if that we are looking only for the length, but you can use the same algorithm for finding out the sequence also. Okay, so I think in this talk, or the lecture, I will just look at the length. Okay. Now say here, what is it that we want to solve? Let's think of it.
LCS
86. Yes, sir.
LCS 86 is all that we want to solve, right?
Yes, sir.
But in the LCS 86, what can we say?
Sir, LCS 86 will be equal to LCS 87.
So LCS 86 is all that we want. 87, okay, let's think of it. Okay. So now see, what is the last one? The last one of both these words is S. Right. So if I have a longest common subsequence of these two strings, I can always, okay, so let me write it here. Okay, so I have said these two strings, okay, say A1 to AN and B1 to BM, and say AN equals to BM. Then what can we say? Then, okay, so maybe there is a longest common subsequence. Can this longest common subsequence be something like this? Say I will just try to maybe this set, 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 this. Can it be possible? Is the four things the longest common subsequence?
No, sir.
No, because we
So
are-
why not?
Because this AN and BM are common, so they.
So A and B are
They
common, so I
will
can
be
always add this AN and BN, and I get a longer one, right? So it must be that the longest common sequence must contain at least one of AN and BN. Okay. Now what happens if I have this one? Say I have this set.
Sir,
And
can you repeat this once more?
Okay. So the longest common subsequence must include either AN or BM. Because if I have a longest common subsequence that doesn't include AN and doesn't include BM, then consider that the longest common subsequence and add that AN at the end. And longest common subsequence that add BM at the end. Okay. So if you want, I can write it actually formally.
Yes, sir. I understood now.
You understood, right?
Yes, sir.
Yeah. So I mean, yeah. So if there is, so if AI1 to AIT and BJ1 to BJT is a longest common subsequence of A1 to AN and B1 to BM, and AIT is not equal to AN, or maybe the opposite one, that's what I mean. If AIT is not equal to N and JT is not equal to M, then consider the sequence says AI1 to AIT and AN, and B1, BJ1 to BJT and BM. Note that these two sequences are same because this sequence is equal to this sequence, right? And this is equal to this. Both of them are subsequence of A1 to AN. Okay, so they are same and are common sequences of A1 to AN and B1 to BM. So which means that, that means that these sequences are LCS of A1 to AN and B1 to BM. But this is not possible, right? Because I have already assumed that these are the longest common subsequences. So this gives us a contradiction. So what is the problem? The problem is right here. That, no, not here. What is it? Problem is here.
IT not equal to N and JT.
Yes. Problem is right here. So it must be that at least one of them must be part of the longest.
Therefore, we can search both of these strings from the end, from both of their ends.
Hold on. It is just saying that at least one of them has to be there. It doesn't say both of them has to be there. Okay. Do you see the problem? What you are saying?
No, sir. Could you please repeat?
Okay. So what happens this one? This is a. Can this be a longest common subsequence?
Okay, sir. Okay, sir. I got it.
So both of them don't have to be there, but both of them can be a common.
Right. So if this is the case, that means the last one. What is this value? This must be equals to AN.
Yes, sir.
So instead of taking this, I could have just taken this.
Right.
And that would have been another sequence. It doesn't say that the previous one was not a sequence, not a longest common subsequence, but this is also another common subsequence of the same length.
Yes, sir.
Okay, maybe you can try to write it formally here also. Okay, so let's say just assuming that only one of them is not there. Then what happens? Okay, so basically you can say that. So what you can say is that I can write the final thing here. So if AN equals to BM, then there exists a longest common subsequence of A1 to AN and B1 to BM containing AN and BN. I'm not saying that all longest common subsequence will contain it, but there exists one that contains it. Fine? Everybody with me?
Yes, sir.
Yes.
Okay, excellent. So in that case, what can we say here? Last string is
yes, sir.
Yeah, last word is same. Both of them are S. So I can say that the longest common subsequence must include this S. Yeah, tell me.
So it will be then LCS of 7,5 plus 1.
Right. LCS of 7,5 plus 1. Now what is LCS of 7,5? Last one is E. Look at them. The E's are same also. So this is nothing but LCS of 6,4 plus 1. Okay. Now what about after that. Now there is some problem. Okay. So here, let's look at LCS of 6,4. So the LCS of these things VILLAG and CITI. Now the last one is G over here and I over here. So they are not same. So at least this much we can say that the longest common subsequence either will have none or at most one. It cannot be both. Both cannot be present, right? So if I want to go back over here and ask, so I have now say A1 to AN and B1 to BM, and AN is not equal to BM. Then what is this LCS of these two strings? Think of the LCS. Can the LCS
Sir, it
constant?
should be maximum of LCS
Yes.
n comma m minus 1 comma LCS of n minus 1 comma m.
Perfect. Exactly. Right. So it can either contain AN or BN or none, but cannot contain both. Right. So I can say, okay, so in that case, there are two cases. Case one, AN is not in the LCS. In that case, the LCS is basically nothing but of LCS of A1 to AN minus 1 and B1 to BM. You have also the case 2. BM is not in the LCS. And in that case, this LCS is nothing but A1 to AN and B1 to BM minus 1. Right?
Yes, sir.
And one of these two cases has to happen. So what is the LCS? It is the maximum of, so LCS of n comma m is max of LCS of n minus 1 comma m and LCS of n comma m minus 1. That's it. Right. And that's exactly what we do. So you have the I and J, they have different values. So you have LCS of 6,4 is nothing but LCS of 5,4 and 6,3. Okay. Now we are getting complicated. So till now we are having a linear thing. But now what is LCS of 5,4? What is LCS of 6,3? It seems that we are now going into a tree kind of structure. But at least we can understand what's going on. So the algorithm can be like this, right? As simple as that. That first of all, you define this one. Now, if AI equals to Bj, then LCS of I comma j is nothing but LCS of I minus 1 comma j minus 1 plus 1. And else means if AI is not equal to Bj, then LCS of I comma j is maximum of LCS of I comma j minus 1 and LCS of I minus 1 comma j. So this is the recursive algorithm. Now, once you have this recursive algorithm, so by the way, this is something where I want you guys to think here, that we have now written a recursive algorithm for this. Okay, this is, as I told you in the beginning of the course, also from the beginning of the. So recursion is one of the most important ideas of algorithms. Okay, and once you have a recursive argument, there are lots of things that you can play with. So of course, one thing that you can say is that, okay, what is the running time of this? Now, if you just try to solve the runtime of this algorithm completely, okay, what you will realize is that, what is it that will happen? You have any idea? See, in the worst case, it will every time this second thing will come up, right? So one of the elements is going down. So this I plus j is going down by 1, right? So in the worst case, so T of n plus m equals to T of n plus m minus 1 2 times. Right. And this, if you keep on solving, this is becoming T of n plus m becomes 2 to the power, in the worst case, n plus m. Again, not a very good idea. Not the runtime of this algorithm is not the best, but it is a recursive. And this is, yeah.
Sir, will you kindly go to that slide?
Yeah.
Sir, so this is worse than the brute force.
This is worse than the brute force.
Okay.
This is worse than the brute force. No doubt about that. But this is where you should.
But sir, then sir, if this is like what we are doing is like a bottom. So we are starting from LCS 8.6, but somehow if we could move from the bottom to top, then we can save those values, right?
Right. So how?
I'm just guessing, sir. I mean, I'm just trying to, because this is what we actually do sometimes, that we tabulate the smaller values and build the larger.
Right. So the idea is that exactly here, right? So you have this the 8.6, right? Let's say I have 8.6. From 8.6, I can go to 7.6 or 8.5, right? From 7.6, I can go to 7.5 or 6.6, right?
Yes. Sir.
From 8.6, I can go to 7.5 and 8.4. Do you see something that is happening? 7.4.
So we need to only calculate the tree of 7.5 once and use
yes, the 7.5 has come twice.
Yes, sir.
Why do we have to do it again? Recursion is making us do it again. Okay. And similarly here also says here this will become 5, 6 and 6, 5. Now 6, 5 here and 6, 5 here. Why to do it again?
So then in this case, the worst time complexity would be nm, right?
Hold on. Yeah, you're right. But so again, as I told you here, so this is what the algorithm things always comes out to be. Okay, you first try the greedy approach. If it doesn't work, try to come up with a recursive one. Recursive one is ideally something like a managerial kind of a job. You want to give your subordinates, you want to split up the work among your subordinates. They will work and you will then take that and solve it. Okay. Now the issue is that if you do it without any brain work, okay, without any brain, then you might make multiple subordinates work on the same thing. So the best way to do it is keep a tab of all of these smaller works so that people don't redo it again. And this is where this whole concept of dynamic programming comes up. So yeah, so this is not good. Use dynamic programming. Dynamic programming has nothing to other than this whole storing this information. Okay. So I have gone over it a little bit earlier, but let me just give you this example over here. Yeah. So we have this thing, right? The idea is that I have LCS I, j is all that I have to solve, right? How many i's? I can be between 1 to n. J can be from 1 to m. So the all total number of LCS quantities that can be there is how many?
M times.
M
times.
Right. So write out a matrix. Okay. How big the matrix? N times m. Now we already just start to fill it up. What all things that can I fill up to start with? The first thing is that you remember we had told that everything 0k and k0 are 0. So these are like trivial things, right? So everything here 0k is filled up, everything here filled up. Okay. Now, what is this quantity? I want to solve this quantity, right? You can see my cursor here. I want
Yes,
to
sir.
know the number here. So this number, because if it is s comma s, it is this quantity here, right? This quantity plus 1. Let's think about it, okay? Now this one is that because of it e and e, this should be this quantity plus 1 also here. So this is LCS64. Now this quantity, because it is G and I, which are not same, it is either this or this. Okay, either this or this. I don't know which one. How do I continue? See, but you realize something is happening. What is happening? I am either moving diagonally or moving upward.
Yes, sir. Or up or
Left.
yes, sir.
Left. Right. So I'm not moving in an orbit way. Right. Every movement is going either up, left, or diagonal. At some
Yes,
point
sir.
of time, I will hit these boundaries. Right.
And then we can backtrack.
Instead of doing that, why don't I start filling it from the boundaries?
Okay. Yes. Yes, sir.
And that's all that we do. Okay, let's look at this one. Okay, C and V are different. So it has to be maximum of this plus this. Not good, useful. C and I is different. It's maximum of this one. So you keep on doing it and you color all of them. Then I and V is different. So this is, so if they're different, you remember it is the top versus the left, right? Maximum
Yes, sir.
of
Yes,
not
sir.
good. Now comes the
That will be
next
one.
one.
Yes,
So
sir.
this has to be 1 because this I and I, that's be 1 more than this. Right? And then you go to here, I and L, okay, different. So this has to be this plus this. So it has to be
1.
1, right? And similarly, you keep on doing it. And you go here. See, note that all I need to do is that I am filling it up in a way that whenever I'm coming to that particular thing, that square, the previous and this one are already filled up. All the 3 things, the top, left, and corner ones are already filled up. So I can just take either a maximum or just add one and get something done. And that's what I do, right? Now here the same thing will happen. And you'll come here, and now we come here. And here I come here and they said, okay, what is E and E? They're same. So it will be the corner plus 1. So 2. And you do this whole thing. That's it. So did you see this nice, very sleek concept that instead of using recursion, but instead of blindly doing recursion, blindly calling subroutines, if you are storing the data in a clever way, you are able to improve it. What is the running time of this one?
M times n.
Order n. Yes.
Order n times m, right? So all that we did was that, so the only few things that has to be told, you have this recurrence, and you tell me how to fill up the square rectangle in such a way that every time I fill up a particular element or square, all the required squares are already taken care of, are already there. Right? I do it and continue. So to fill up any one square takes a constant number of times, and there are nm squares, and that's it. So this is dynamic program. Okay. The recursion remains same. Okay, it is just the way of storing the data that is helping in the saving of the time. Okay, this is something very, very, very important. This is something, and whenever you think of an algorithm, always think like this. So that's why I always tell my students to think recursively. If you can't think greedily, or the greedy algorithm is not giving you these things immediately, think recursively. Even if the recursive algorithm doesn't work, maybe the dynamic programming technique by storing the data correctly will work. Okay. Now, okay. Now I just did everything by how I told you how to compute this longest common subsequence. But what happens if I ask you to actually produce you the longest common subsequence? Can you do that?
We store the values where the I increases.
That is one good way of doing it. Okay. Or you can even here, you can store the longest common subsequence every time. Instead of 1, you can say that, okay, I want to store the longest common subsequence. Okay. So you can actually store the pointers in the table. And by doing so, you can get the longest common subsequence. So, yeah. Okay. So I know that this concept of dynamic programming can take some time to really grasp. So that's the reason why I will be spending even one more day on this thing, one more lecture on dynamic programming kind of concepts. Okay. And it will be kind of, I mean, much less than what actually is done in modern day applications and all. There are dynamic programming on trees and all that you can play, where you don't store things in a square or rectangle, but store things on the vertices of a graph or tree and so on. But the main idea is basically this. You have the recursive algorithm, right? So recursive algorithm basically says that you can somehow make your subordinates solve some problems, and you can combine their answers to finally get your actual solution. Right? Now the subordinates can also split up and divide the problem into their subordinates and so on and so forth. It's something that is done in any factory, any industry, any IT companies everywhere, right? There's a manager who splits up the job and tells various subordinates, do this, do this, do this, do this. Then they break up the work into smaller parts and make them do it. Now, if you keep on doing it in a very brute force way, you will find that maybe in TCS there are thousands and thousands of people just coding up simple binary search algorithm kind of stuff like that, or simple subroutine that everybody is using. So instead of doing such kind of a brute force kind of a not brute force, some kind of stupid kind of a breaking up with this whole thing, everybody stores what they have done in some common place. So if someone has solved a problem already, no other person needs to solve that problem. That's all.
So in a sense, in a recursion algorithm, we can notice that the flow of the sub-problem solving is like a tree where there is some parallel computation that can take place. But in dynamic programming, it's mostly sequential. Here,
no. So what happens is the case of for any recursive algorithm, okay, what happens? You have the main person, okay, you have this work. It is split up into 3 parts or 4 parts, right? Now, these 4 parts has been split up into another 3 parts. Say, here they have given it to 2 parts and so on, right? It is correct that it looks like a tree, okay? But who told us that this work and this work is not same?
Right, there is no communication amongst these subordinates.
There is no common communication with the subordinates, right? Although they are solving the same thing.
Right.
So the dynamic programming just says that if you are here, try to just store this data somewhere.
Right.
So that whenever this person needs it, he can just go and find it out and not do the computation.
Yes, sir. So,
Okay.
sir, what I was trying to say was, suppose that we had the resources to do computation parallelly. Let's say we had
Yes.
k number of computers working on
Yes. Yes.
such a problem, then probably recursion could be much faster, right? But
Probably
then
recursion is much faster. Okay. So
Right.
then recursion is much more faster. But then also see again the same thing. Whenever you are doing the same task by multiple people, you can clearly see that there's a wastage of resources.
Yes, sir. Right, right,
So I mean, however you want to think of it, it's a wastage of resources.
right. But then
Right.
I was saying that if we you had the same number of computers and they were
I
trying to do
understand. It's like so. In that case, the total time taken will be less,
right,
but the number of computers required will be more.
right. Agree.
Okay, so in terms of the resources requirement, there's a lot of wastage, right? So dynamic programming is all that is saying is that try to store this data in a nice compact way somewhere so that it can be used.
Yes.
Okay, so your job is just to so this thing of this square rectangle thing is just our way of saying that, see, if you store the data like this, we will be able to reuse it.
Yes.
Okay, how you are storing the data and how to reuse it is up to you. You can store it in a this rectangular grid. You can store it in a straight line grid. You can store it in three-dimensional grid. You can store it as nodes of a graph. Okay.
Yes.
That is up to you. But the main concept is you store it in a nice compact way so that when somebody else needs to do the subroutine, they can do it.
Okay, right. Actually, sir, with this matrix form, it's quite clear the actual depth of these intersections in the regular recursion method. Because here, if we just visualize what the flow of that tree would be in this matrix form, we can see it will be intersecting almost like a parallel grid, like a lattice grid.
Correct.
And there will be quite a few intersections, right?
Yeah, there will be lots of common. There's a lot of same work being done multiple times.
Right.
Okay, so so here are some questions that are there. Okay, so how can one find longest common subsequence between three strings? And how can one find longest common subsequence between k strings? I mean,
So here, instead of a two-dimensional matrix, we can take a three-dimensional matrix.
Yeah, think of I mean, yes, try to kind of write it up properly. Okay.
Okay.
And then, so whenever you tell these dynamic programming algorithms, like let me tell you very clearly over here. Okay, this is what you say, right? Fine. But when you are saying here, right, you have to kind of tell me how you are filling up the squares. The recursion is what my advice is to call this. Recursion is the head of the algorithm. Okay, but how you are planning to fill up the thing? Oh, sorry, recursion is the heart of the algorithm, and how you are filling up these rectangles. Okay, so for example, are you going I from 0 to n, or are you going from n to 0? Are you doing from j equals to 0 to m or m to 0? Okay, I mean, under what is the way in which you are filling up this rectangle? That is the main head of the dynamic programming techniques. So basic idea is that when you're trying to solve such problem, all the other data should already be available.
Yes, sir.
Okay. Okay, so let's say another kind of common problem or similar problem. It's called longest increasing subsequence. Okay, so what is the longest increasing subsequence? So this is a number. Okay, so I have a sequence. You have a subsequence. So I have a sequence of integers, say. Okay, say I have a sequence of integers, say 9, 2, 5, 6, 1, 9, 8, 7, 9, 3. Now, a longest, so what is the subsequence? Again, the subsequence you understand, right? But what we are interested in is the increasing subsequence. What is the increasing subsequence? So 2, 5, 6, 7, 9. That's the increasing subsequence. So the subsequence, they keep on increasing. Okay, so maybe another one can be like say 1, 8, 9. That can be another increasing subsequence.
Sir, do we know the range of the numbers?
No, we don't know that. You can think of them. I mean, it doesn't matter. Okay, let's think of it that they are integer between 1 to 10. 1 to 10.
Okay.
Okay, so that would not be a big issue here. Okay. So the job is to, given a string of integers a1 to an, find the longest subsequence that is increasing, the longest increasing subsequence. Now, can somebody want to take a shot at it? Think about it. Okay, there are quite a few interesting solutions to this.
So I think I
You know the solution? Okay.
Yes, sir.
Do you know a dynamic programming algorithm?
Divide and conquer algorithm, I think I know.
You know divide and conquer algorithm?
Yes, sir. So the basic idea was something like if I divide the sequence into two parts, so the longest increasing, oh no, sir, that was a slightly different problem. So that's in that problem, we have to find the continuous increasing thing.
Yeah, but this is not.
Yeah, yes, sir. Sorry, sir.
You guys can think for a couple of minutes. There's some pretty, yeah.
Sir, hello.
Yeah.
So similarly, like the previous problem, we can construct a matrix of length n cross 2, where the two column will store 1 and 0. Means if that a particular AI is there in the longest subsequence alone, and then we can go by that process.
You learned what?
Sir, I'm saying that first we'll construct a matrix n cross 2. And for each I, say AI, the L, suppose the matrix is M. Suppose the matrix is M, then MI0 would be the length of the largest, would be the length of the longest increase in subsequence, excluding the number AI in it, and MI1 would store the the length of the longest increase in subsequence with the number I, with the AI in that sequence, and ultimately we will report the maximum of M n0, M n1.
Okay, I think you are thinking in the right direction, but okay, so I would like you guys to go, think about this one. Okay, I think you are kind of, yeah. So the main idea is to break it up. Yeah.
So the longest, let's say L of I be the longest subsequence that is starting from AI.
Right.
And L of N is 1. And okay, so we start from the last thing. Okay, L of N is 1. Like the longest string starting from AN is just AN itself. So L of N is 1. And so then we fill up L of N minus 1. So that is 2 if an minus 1 is strictly less than or equal to an, or otherwise it is equal to L of N.
Okay.
And for any I, we know L of I is 1 plus maximum of L of J, such that J is strictly greater than I. like the longest.
Yes, I agree. So I think you guys, you are thinking in the right direction. Okay. So I would like you guys to go. I mean, I think your thinking is correct. Okay. So I would leave this one as an exercise for you guys to go and write down the recurrence properly, prove the correctness of the recurrence, and write the dynamic programming and trying to understand what is the time complexity. Okay. So I think maybe a couple of you have some very good ideas about it, but so I let you guys think about this particular problem. But sometimes, so I will give you another solution to this, which is completely different. And this is something that we will come across sometime in future, maybe in 2 weeks time from now. Okay, so let me say this way, that I want you guys to go home and solve this LIS using DP. Okay, so homework is LIS, longest increasing subsequence, using dynamic programming. This is something that I want you guys to go back and do it for yourselves. So find out the recurrence and prove that the recurrence is correct. Tell me how you will fill up the matrix, and then finally, so these are the things that I want you to do it. Okay, write the recurrence, proof the correctness of the recurrence. Number 3 is how to fill up the matrix. I mean, I'm assuming that you will fill up a matrix. If you want to fill up something else, that's also fine. And the time complexity. So I want you to do this one. Maybe this is something that the TS possibly will cover in the tutorial in Friday. Okay. So please go back and think about this problem. But now, what I am going to do is keep a different algorithm. Okay. See, one thing that you should realize is that the art of doing well in life is to be lazy. Okay. If lazy doesn't mean that you have to not do anything, but you have to learn how to reuse things that have been done already. If somebody has done something, it is not a very good idea to reinvent the wheel. Okay? And in algorithms also, the same concept works a lot. So in algorithms, we call this thing called reduction. This is something that we will formally define it more carefully, again, 2 to 3 weeks down the line. But the basic idea is that if you want to solve a problem, sometimes it is easier to reduce this problem and to a different problem, which we know a solution of, and reuse that. So instead of,
so we can sort this and then find a common
difference.
Oh, yes, sir, we can do that.
So here, for example, so I have this example of a longest increasing subsequence, right? And this is the longest increasing subsequence. Now, one thing that you realize is that this longest increasing subsequence is increasing, right? It's in one direction, right? Now, of course, you can find this one using dynamic programming. But then there's another thing that you can do. You just sort this string. Say the sorted string is B1 to Bn. Now, if I find the longest common subsequence between B1 to Bn and A1 to An, what do I get? It's a common subsequence. That means it's the subsequence of A1 to An. But it's also a subsequence of B1 to Bn. That means it is increasing, therefore. So a common subsequence between A1 to An and B1 to Bn has to be a increasing subsequence of A1 to An. On the other hand, right, if there exists a longest increasing subsequence here, now that's an increasing one, so that has to be also be a subsequence of B1 to Bn, right? And therefore, it has to be a common subsequence of A1 to An and B1 to Bn. So in other words, the longest common subsequence of A1 to An and B1 to Bn is nothing but the longest increasing subsequence of A1 to An. Okay.
Sir?
Yeah.
Sir, this algorithm has the time complexity big of n squared.
Yes.
And the one just told by Ritu Prata, mentioned by Ritu Prata,
yeah,
it was in linear of big of n, right?
So think about it.
Sir, why big of n log n?
So n log n is for sorting and order n square is for this one. Okay, so I am not going to, so whatever you guys suggested, okay, they are correct, but you go and do these things correctly. Okay, so it might be possible that you can get something better than this. Okay, but most likely your algorithm will be order n square. Okay, so do the time complexity calculation carefully. Okay, so the issue that will happen is that why don't you do that? Okay, and let me know what algorithm that you get here.
Okay, sir.
Okay, so this is basically what we did here today. Was we used a new concept of dynamic programming to solve a problem. Okay, and after that we have seen another thing of the reduction, how we can to reduce one problem to another, or use one problem to solve another. Okay, so these are the two things that we have done today in class. Please go back and try to solve this LIS using the dynamic programming by yourself. Okay, in the next class we will again do dynamic programming, but on a different problem. Okay. And that time it will be like you will be doing it more than what I will be. I mean, like I will make you guys do it. Okay, and then you have the tutorials also on Friday when the dynamic programming will be done. So dynamic programming is a very beautiful concept, but it will take some time for you to grasp or learn the tricks of how to actually solve a problem. When somebody gives you a solution, it is easier to follow that. Oh yeah, this is what is happening. But actually coming up with the dynamic algorithm problems can become a bit more tricky. So I will be posting a list of problems where the dynamic programming will be used. But irrespective of that, I would request you to take a look at some of the books or any of the books that you have got and go over the dynamic programming chapters of that. Okay, so there are lots and lots of exercises. Try to solve them.
Sir, I have a small request.
Yeah.
Sir, is it possible, let's say for example, for the problem set, one problem set will be given for DP, right?
Yeah.
So is it possible that even that to post it like at the start of the week, let's say even on Monday, so that we can have, like 4 or 5 days before the tutorial where we can actually get, like, if we put in, let's say, sometime every day, we will have ample time to at least go through the problems. And most of the times what happens is when the assignment, when the problem set comes and when the tutorial session is there, I mean, there is always a little less time.
Okay, sure. I mean, we can do that. Okay.
So then we can see it, and then we can, I would be more, I would say more we will be participating a bit more in the
okay
class.
So for this problem, this tutorial, okay, I would like you guys to go and think about this LIS problem. Okay, and that will be discussed. If you have any other questions, okay, on dynamic programming particularly, that would be something that I would really request you to come here. I will try to post a collection of problems in dynamic programming, maybe later today or something like that, and let's see what happens. Okay, I will try to, but again, see, just because if the tutorial session is next week also, it doesn't mean that you cannot ask questions of dynamic programming. The tutorial session is there because of that. You can ask the TS to solve any questions of the previous problem sets and so on. Okay, so if you don't ask, then they continue with whatever they have prepared for or something. Okay, is that fine?
Yes, sir.
Okay, so I think I will stop here. Today was a short class, but I mean, I believe that you guys will take some more time to grasp this whole concept. So I'm not going to really force too much things on you guys. Okay, so this, I mean, dynamic programming is exactly this kind of a problem, a subject where the solutions looks trivial. But it is more important for you guys to think about how did the solution come? So how will you come up with such a solution? Okay, so that things you should slowly start doing it. So I'm leaving you early, hoping that you guys will think about whatever has been done in class, try to solve this LIS, and if possible, look at some of the books. Okay, so chalo, I will see you on Thursday.
Sir, when will in-class classes begin?
When will they?
IRL classes.
What classes?
Offline class.
Oh, offline classes. Okay, so how many of you are back in campus? Who is back in campus?
So many of the students are.
Can you please tell, sir, what was the scenario today in the first class?
I did not go to the class.
No, sir. No, sir. I'm asking Shurjatapu. I mean, we had the offline class in the first session today.
Yes, around 10 people came on in the classroom, I think.
Okay.
But a class has been assigned and all the cameras are present.
Class has been assigned. There's no doubt about that. How big is the board?
There are 2 boards, in fact.
Huh?
There are 2 boards, and one board is visible completely, and another one is visible partially.
So for the students.
Yeah.
Yes, sir. Partially.
There are projectors also in the classroom. The classroom has projectors.
Classroom has projectors. See, I mean, I have no problem in teaching in the classroom. I'm a bit more worried about the people who are offline, actually, or online.
There's a camera for them.
Is that good enough?
Yes.
Sir, you can at least give it a try, maybe in the next week.
Okay, so let's see. Next week, then I can take a shot at that. Okay. I don't think I will do it in this week. Next week or next to next week, I will try to do it. But what I can do is that if you guys are there, so I can at least for now I can assign a couple of hours, maybe even every day also for that matter, so that you guys can come and meet me and have physical doubt clearance sessions and all those things. But the people who attended the class offline, So this one, of course, was much better for you guys, right? I assume so.
Yes, sir.
But if you guys had asked, did you ask questions or did you not ask questions?
To whom? To the sir?
To the instructor?
Yeah, I mean, he was present in the classroom also.
Yes,
We
he
were
was
all-
present in the classroom and you asked questions. Now, those questions were audible to the online people?
That we, I think somebody who was online can answer that.
That's what will be a problem actually.
That will be a problem. It will not be audible. Sir.
You can reiterate the questions clearly then.
Sir, we could hear from the professor, but not the problem which was asked by students.
Actually, this problem
Sir,
can be solved.
I prefer this mode of teaching actually, means at least for the algorithm course.
You prefer this over the offline one? Hello?
Yes, sir. Yes, sir.
Yeah, so let me see. I understand that. I also prefer. I prefer offline classes, no doubt about that. But this hybrid class is something that I'm not exactly sold into that idea that much. But otherwise, I have no problem presenting it. So I will happily have a physical meeting with you guys, even having some tutorial sessions or other sessions of problems, discussions and all in an offline fashion. That I will be happy to do it. About taking classes in these things, I will take a shot at it next week. I will see if there's something more, what are problems that I face, and if not, then yeah, we will see what can be done. Okay, so anyway, next class will be online only, and this tutorial will also be online. So for people who are in class, first of all, by the way, I am coming to the institute every day. My office is in the PGA building, 6th floor. Okay, and I am coming. This dinosaur building.
Okay.
Okay, so I am there. So, and I'm usually there from 11 o'clock to 4 o'clock for certain. I'm there for longer time also sometimes. So please drop by anytime you have any questions and doubts and all. I'll be happy to meet you guys physically, and then we can, whoever you guys, I will be happy to discuss more with you guys. For the class, let it be online for now. We will see about it, how it goes next class, next week. Okay, is that fine?
Yes, sir.
Yes.
Yes, sir.
Okay. See you Thursday.
Thank you, sir.
Thank you, sir.